Alright, in the last video we looked at circuits, either series or parallel, and how that affected the amount of current that got to a light bulb or a resistor. In this video, we're going to look at what happens when we combine both series and parallel into the same circuit. And this is really more practical, since typically what we're trying to do when we build an electrical circuit is get a very specific amount of current to a certain location in order to generate a certain amount of power. So it's a little bit more complicated than just simply putting something in series or something in parallel. So I'm just going to do an example of a more complex circuit that combines both the parallel and the series. All right. So what I'm going to do is I'm going to go ahead and I'm going to put a resistor here that is going to be in series with two resistors that are in parallel with one another. Right? And let's say that it's a 12-volt battery, and I'm just going to make up amounts. Let's say I've got this one is 6 ohms, and let's say this is 3 ohms, and this is 2 ohms. All right? So essentially what happens is when I turn on the circuit, we're going to have a current that flows through the entire circuit. This resistor right here, the one in series, is going to get the entire current, but these two that are in parallel are going to have to share. Now, if we look at the amount of resistance, we can sort of qualitatively answer a few things. We know that all of the current is going to go here. When it splits off here, though, it's going to follow the path of least resistance. So we should actually have more current going through the 2 ohm resistor than the 3 ohm resistor. So this one should actually be brighter than this one. So how do we go about solving this circuit? Well, always whenever we approach a circuit problem, the first thing that we're going to do is we're going to try and figure out what is the equivalent resistance or the total resistance. So I have two parallel circuits that are in series with this. So the first thing that I have to do is I need to figure out, well, what is the total of these that are in parallel so that I can add it to this one that is in series. So remember, using parallel math, we're going to say, well, 1/2 plus 1/3 is equal to 1 over our equivalent. And this is pretty easy for me to do in my head, so I'm just going to make them like fractions. So we're going to have 3/6 plus 2/6 is going to give me 5/6, and then I take the inverse of that, which is 6/5. Okay, so I take the upside down, so 6 over 5 is the total number of ohms, and let's turn that into a fraction. That's to a decimal. That's 1.2 ohms. So these two together are 1.2 ohms. Now this is in series with this, so I would have the 6 ohm resistor plus the 1.2 ohm resistor, and so my equivalent resistance for the entire circuit is going to be this. That is 7.2 ohms. So then I could find out the total current. Well, total current, I would take total voltage over total resistance, so 12 divided by 7.2, and I get 1.67 amps. So 12 volts over 7.2 ohms gives me 1.67 amps as my total current. Now, I said that the total current goes through here, right? Because there's only one path for the current to follow when something is in series. So the amps here is going to be that 1.7 amps. Now you can see that I have resistance and I have current. I could also then calculate the voltage that is in this resistor. Remember that those that are in series share the total voltage. So the voltage here plus the voltage that gets up here has got to be equal to 12. So if I just take 1.67 and multiply it by the 6 ohm resistor, I get that 10 volts is being used up right here at this resistor. So that means that 2 volts are getting to the parallel part of the circuit. Now, if you remember, in a parallel circuit, each one of them gets the same voltage. So we're going to have 2 volts here and 2 volts here. Now what this allows me to do is it allows me to figure out, well, how much of this 1.67 amps is going here and how much is going here. Remember, we said more was going to be going to this than to this one. So I've got volts and resistance, so I just divide them. Well, 2 over 2, that's easy. 1 amp is going here. And then that means that 0.67 amps would have to be going here, which is what 2/3 is. So 0.67 amps. So based on this circuit, but just by using sort of a resistance math and doing Ohm's law over and over and over, I have figured out the total resistance, current, and voltage for every single circuit in this combined resistor.